Alrighty, here we go again. So let's keep going back with our section 1.8 exact ODEs, right? So you tell me, right? Now what are we doing? We're going to do a homework problem. Woohoo, right? This is our homework problem we're going to do. But before we do that, let's fill in the ideas. So with an exact differential equation, what is the idea? You write it in this differential form. Some function of x and y times dx plus some other function of x and y times dy is equal to 0, right? What do you check? Well, you could try to memorize and make a mistake, or you can just remember where it all came from, right? That this guy, right, came from taking that derivative and thinking about we know our solution, right, is going to be, if we do have exact, f of x and y equal to a constant, right? So we took the derivative with respect to x, and we came up with this guy is our partial f, partial x, right? And then what sits here next to the dy is the partial f, partial y, from taking that derivative with respect to x, right? Okay, and so what do we want to check? Well, what we want to check is that fxy is equal to fyx. That's what we want to check, right? That the mixed partials are the same. So what is that? What is fxy? Well, that is my, right? The partial derivative of m with respect to y. And what is fyx? Well, that is nx. Partial derivative of n with respect to x. That's what we want to check, right? As long as everything was nice and continuous, right? Because that's what our theorem required. And so this is the thing that you want to check. You could try to necessarily, memorize it, but it's really better to understand where it came from and what it really is saying, right? Mixed partials, the second partials, mixed partials of f are equivalent, right? Doesn't matter the order. Okay, so what's the deal, right? Okay, you check this. Is this true, right? Okay, if this is not true, right, if false, right, if not true, if false, then you can cry, basically, because if you've already gone through linear and separable, now you're out of luck, okay? If false, get clever. Now really there's other things you can do. You can create integrating factors that turn an equation that's not exact into an exact differential equation. Some of that is also in this section in 1.8. We're not going to do that piece. Feel free to read as much of that as you like and just see how you can, if it's almost exact, you could turn something in, you could come up with an integrating factor just like we did with linear, multiply your equation and then come up with something that is exact. So this is what we check, right? If true, then we're excited. If true, yay, exact. Now usually exact though is your kind of last resort. You've already looked for linear and separable because it's just simpler to do those problems, right? It's just simpler, right? So you're already sort of at your last spot with getting to exact. So here we go, right? Let's see, does this guy look linear to you? No, right? We got e to the xy up there, we got y up there, and the inside the argument of the exponential function, not happening, right? And we got this multiplication going on, right? Okay, not linear, not separable, okay? You're not gonna be able to separate these guys out from x and y's, and so you really are stuck with nothing but exact, right? Okay. It's screaming exact at you if you listen. So what are we going to do? We want to write it in the differential form like this first, right? So what does y prime mean? Okay, I'm just going to save myself some time. Right? It means the derivative of y with respect to x. Yes? Okay? And now we want to rewrite this guy in this form. And so we're going to have all of this stuff, cosine x plus y e to the xy dx plus x e to the xy dy is equal to 0. Now we have it written in differential form, okay? And so it's again not hard for us to recognize, oh, this guy is my m okay? And this one is my fy, which is n, because it was fx dx plus fy dy. We know where that came from, right? All right, so let's take a look. Okay, so m is cosine x plus y e to the xy. And we want to compute my, right? So let's test for exactness, okay? So our goal, and n is x e to the xy, and our goal is test for exactness. Is it worth going through all of that work, partial integrating and then differentiating to try to come up with the function f? If the function f doesn't exist, it's not worth going through all that work, right? And it's awesome that we now have this test for exactness so that we know ahead of time that we don't have to go through that work and then end up with something that makes no sense. Some function of x is equal to stuff that depends on y, and you can't do anything, right? All right, so what's our test for exactness? So let's compute my, right? So what is my, right? It's the partial derivative with respect to y of our guy m. And what is m? Cosine x plus y e to the xy, right? Okay? Okay, so let's take that derivative, right? What is the partial derivative with respect to y of cosine x? Yeah, beautiful, 0, awesome, okay? Plus, what about that guy? Partial derivative with respect to y of y times e to the xy. Y times y times means I'm going to have to use what rule? Good. Product rule and chain rule. Lots of fun, right? So let's go with product rule, right? Partial derivative with respect to y of this product, right? The first, they both depend on y and taking derivative with respect to y. That's why it's product rule. The first times the derivative of the second, right? What's the derivative of the second? The second is e to the stuff. So what's the derivative of the second? E to the stuff times the derivative of the stuff. The derivative of the stuff with respect to y. What is the derivative of xy with respect to y, pretending x is constant? Good. X, right? Yeah? Okay. So, first times the derivative of the second plus the derivative of the first. What's the derivative of y with respect to y? Good, just 1, right? Times the second. Okay, so there's my. My is yx, I'll just write it as xy because we often like writing the x in front. Xy, e to the xy plus e to the xy, right? Or e to the xy times xy plus 1, yeah? All right, what about nx, right? That's what we want to compute. Nx, n means take the partial, nx means take the partial derivative with respect to x of n. What was n? X e to the xy. You guys are excited, right? Because you're going to do a what? Another product rule. Yay, right? Because it's a product of two functions of x. We're good at this now. What do we got? First times derivative of the second. Okay, what is the derivative with respect to x of e to the xy? It's e to the stuff times the derivative of the stuff. Now the stuff is x times y. We're pretending y is a constant, taking derivative with respect to x. So what do I get? Yeah, y. Nice. This is looking good, right? First times the derivative of the second plus derivative of the first. What's the derivative of x with respect to x? Good. 1 times the second. Life is good here. What do we get? Right? We've got xy e to the xy plus e to the xy. Yes, that's what nx is. And so lo and behold, so yes, my does equal nx. This equation is exact. This ODE is exact. And we're super happy about that, right? My is equal to nx. So now what do we know? We know that its solution, right? So therefore, I'm just going to come here, right? Therefore, the solution of this ODE x and y for some potential function, f of x and y, we don't know that function yet, is equal to a constant, right? Okay? So, these guys, these level curves are solutions of this differential equation. Our job now that we know it's an exact equation, is to come up with f of x and y, right? That's our job. I'm gonna erase this now. So we know that our integration process is gonna work, and it doesn't matter which one we start with. So last time, I think we started with integrating with respect to y, so maybe this time we'll integrate with respect to x, okay? So we've got it, we're golden, so now what do? Now determine f of x and y, okay? That's the next piece. Okay, so again, remember, what do, right? Well, as long as you remember these pieces, right? As long as you've got this knowledge, you know you could either go to m and you integrate with respect to x, or you go to n and you integrate with respect to y to get f, right? That's what you do, okay? Because you understand where they came from. So, we said we're going to integrate with respect to x first. So this time, let's integrate with respect to x first, this time. Because it doesn't matter. Now, some problems, it might be easier to do one or the other of the integrations first. And you might run into a really hard integration if you do one of them first versus the other. So sometimes you have to pick judiciously which one to go with. And sometimes it just doesn't really matter. The integrations are basically the same, and you know, it's just a different way to get to the same endpoint, okay? So let's integrate with respect to x first. So if we're going to integrate with respect to x, right, we want to integrate m, right, okay, with respect to x, right? We're kind of doing a partial integration. So remember, remind yourself of that. Remember, so what would I think here? I'm integrating with respect to x. M, what was m, right? It was partial f partial x. Fx, yeah? And so if I integrate that guy, I'm going to get my function f of x and y, okay? So my f of x and y is going to come out of that. So what am I going to integrate? Okay, what was m? M was the guy multiplying dx, right? So my m is this. Cosine x plus y e to the xy. I'm integrating with respect to x. And I'm remembering to myself, this is a partial integration, right? So I'm not going to get a plus c when I'm done with this integration. I'm going to get a what? Plus, I think I heard it. We'll wait until we get there. Okay. So, what's the integral of cosine x with respect to x? Good. Now you check. What's the derivative of sine? Cosine. Good. Whew, yay, we did it, right? Okay, now what? Okay, now we're integrating y e to the xy with respect to x, right? We're integrating y e to the xy with respect to x, yeah? We could like kind of do that over here, right? Let's think about that. Integral y e to the xy, right, with respect to x. I'm wondering if you can see over there, actually. Maybe. Let's just do it down here. Okay. We're going to do it in blue. Okay, so that piece. It's going to do it down here. The integral with respect to x of y e to the xy with respect to x. Okay? Partial integration. Well, if you were doing this problem, you might be thinking like it's really like a U substitution, right? So, you know, you've got E to stuff, let U be the stuff, right? Okay? So I'm integrating with respect to x, right? So what is the partial derivative of U with respect to x? Partial derivative of U with respect to x here is, good, y, yeah? Okay, So what does that mean? This is derivative notation, right? We can write it in differential notation. So we've got partial u is y partial x. Yeah? So this guy is really an integral with respect to x. Well, this piece, y partial x, is really just partial u, right? And this is e to the u. Yeah? Right? Well, what's the integral of e to the u with respect to u? Right, e to the u, right? Plus c, okay, but we know, we're just going to say plus something right there right now, okay, yeah. This is one of the partial. So what was u again? U was xy, so that's e to the xy plus what? That's the question, okay? You guys tell me. So we got sine x plus e to the xy plus, I integrated with respect to x. I really have functions of x and y going on. What acts like a constant? Y. So what do I have? Some whole function of y. H of y, g of y, f of y, it doesn't matter, right? Instead of plus a constant, I've got plus some function of y, right? Just like in the last problem, when we did the other example, we integrated with respect to y first, and we got some plus some function of x, right? Okay. So, now what? We have our, remember, what were we doing? We were getting an expression for f of x and y. We made a lot of progress, right? This is the solution. That thing equal to a constant, right? But we still have this unknown function in there. We can't have an unknown function. We want it to be explicit. What do we have to do, right? So the first thing we did was integrate with respect to x. So since we did that, what's our next step in this one? Good. Differentiate with respect to the other variable, y, right? So I've got my guy right here. Here's my f. So now let's take the derivative. Take the derivative with respect to y of our new f, of our f we just computed. Right? So I'm going to take the partial derivative of this guy with respect to y. What is the partial derivative with respect to y of sine x? Good. Zero. X is a constant. There's no y's in there. That derivative with respect to y is 0. Now I've got plus e to the stuff. What's the derivative of e to the stuff? E to the stuff times the derivative of the stuff, right? I'm taking derivative with respect to y. So what's the derivative of xy with respect to y? Partial derivative of xy with respect to y. Treat x like a constant. Good. So I get x. Yes? Okay? Partial derivative of 5y is 5 with respect to y, right? Same thing. So I've taken that partial derivative. Now what's left? What's the partial? Well, this is an ordinary function, right? So what is partial derivative with respect to y of h of y? Well, that's just dh dy, ordinary derivative, or h prime of y. Yeah? Okay? So we found our function, we integrated, defined our function, then we took the derivative with respect to the other variable to get what partial f partial y is. But we know what partial f partial y needs to be. It needs to be n, right? If we're going to have this type of a process, then that had to be n. And so therefore, we set that now equal to n. Because n is fy. It has to be fy, right? What was n? N was x e to the xy. Yeah? That's what n is, right? Yeah? And so, now what? We have this equation right here to solve for h prime. And thus h, right? Well, that equation is pretty awesome, right? Because, lo and behold, what happens? X e to the xy on this side, x e to the xy on that side. What does that leave? Right? H prime of y is just zero, right? Make sense? That's awesome. Now, if there were extra x's left over here, we would have had made a mistake somewhere, right? If it was like plus x squared. You can't say h prime of y is equal to x squared. That makes no sense. This is a function of y only, and this would be x. If it was x squared, there would be x's over here. That would tell you you made a mistake somewhere. Either you made a mistake in your integration, or you made a mistake in checking whether the equation was exact or not. Okay? All right. So we get h prime of y is 0, so what does that mean h of y is? It does mean h of y is a constant. I heard you guys say that, right? H of y is a constant. The derivative is 0. The function's a constant. But what are we going to do with our function? Right? We're going to set it equal to a constant. So when we're doing these guys, we always take our constants to be 0 because we're going to set it equal to an arbitrary constant anyway. We don't need 3 arbitrary constants floating around, right? Okay? So h of y is 0 because of that. Maybe I'll just write it like this. H of y is k, where k is any constant. So we'll take k equals 0, right? So h of y is 0 because we're going to set it equal to a constant anyway. Yes? So therefore, what did we just discover? This piece was which the only thing that we didn't know yet, right, is 0. Here now? You okay? Okay, okay? Therefore, our f of x and y is sine x plus e to the xy plus, what did we discover that to be? 0 in this case, right? Nothing, okay? Okay. So f of x and y, the potential function for this differential equation is sine x plus e to the xy. The solution of the differential equation is what? That is equal to a constant. Okay? Yeah? Make sense? Okay. Let's see. What else could we mention? Suppose we had an initial value problem. Okay? Suppose we had an initial value problem. So we had, what would be different? Nothing. We would just go right through this exact same process. We all went through, get that implicit solution, right? This is an implicit solution. Yeah? Okay? And what if we have the initial value problem, just making this up now, right? Y evaluated at pi over 2 is 4. Okay? Well then, what would be our solution of the ODE is sine x plus e to the xy equals c, right? The initial condition would allow us to determine c, okay? So what would be IC, right? Let's apply the initial condition. Okay, well, x is pi over 4 and y, or pi over 2 and y is 4, right? So sine of pi over 2 plus e to the pi over 2 times 4 is c. What's sine of pi over 2? Yeah. 1. plus e to the 2 pi is c. Yeah? It's a perfectly fine c. So what is the solution of the IDP? Solution of the IDP is sine x plus e to the xy is equal to 1 plus e to the 2 pi. Make sense? There we go. Okay? Alrighty. In the beginning of the section, there's an example with concentric circles as your level curves, right? And so for those guys, if you are, if you think about a concentric circle, right? Okay, x squared plus y squared is equal to c, right? Circle of radius square root of c, yeah? These are all circles, yeah? Okay. And then depending on, if we leave things in implicit form, then you could write things, you know, suppose we want the solution that goes through that point, right? Okay, then we would have the whole circle. But if you're asked for a y equals form, right? If you want an explicit form, y equals, well here, right, if we're gonna solve this for y equals, you've got c minus x squared square root plus or minus, right? Okay, and then if we want the explicit form, then we've got to pick either the top half of the circle, right? That's the plus piece, or the bottom half of the circle. That's the minus piece, right? Depending on where the initial condition is, right? Okay, so you only have a minus piece if you were down here. If you want it written in explicit form, and in implicit form, you would have to. Yeah? Okay. So those are just some things I thought would help as you work through some of these problems. Oh, let me mention one more for you before we close out here. Another one of your problems. Let's look at this one. 101C. Okay. E to the x plus e to the y dy dx is equal to 0. Should I dive into, what do we do? What do we do to solve this while I'm erasing the board? You look at that one. What do you do? You could try exact, but it's separable, right? Much faster. Separable, much faster. Yeah? Right? So, I don't know. I think separable is much faster. But anyway, think about all of those things as you are doing your problems. Remember that you really also want to be analyzing every equation regardless of what section it happens to be in homework. Because you want to get good at identifying which of our 3 methods of solution for first order ODEs, separable, linear, or exact, is the right one to go for our particular problem. All right, we will see you back again sometime soon.